Give a short response to the following questions. When a motorcyclist hits a stationary car, he may fly off the motorcycle and the driver in the car may get a neck injury. Explain. Answer. When the motorcycle suddenly stops after hitting a stationary car, the rider's body tends to keep moving forward due to inertia, Newton's first law. This causes the rider to fly off the motorcycle. The driver in the car experiences a sudden jerk, causing the neck to snap backward and forward quickly, leading to a whiplash injury. In autumn, when you shake a branch, the leaves are detached. Why? Answer. When the branch is shaken, it moves, but the leaves tend to remain at rest due to inertia. This causes the leaves to detach and fall. Why is it not safe to apply brakes only on the front wheel of a bicycle? Answer. Applying brakes only on the front wheel causes the front wheel to stop suddenly while the rest of the bicycle is still in motion. Due to inertia, the rider and the rear of the bicycle may flip over the front wheel, leading to an accident. Deduce Newton's first law of motion from Newton's second law of motion. Answer. Newton's second law, F equals ma if F equals 0. Then ma equals 0. A equals 0 as m is not equal to 0. A equals 0 means there is no change in motion. This implies either the body is at rest or moving with uniform speed in a straight line. This is Newton's first law. Action and reaction are equal but opposite in direction. These forces always act in pair. Do they balance each other? Can bodies move under action-reaction pair? Answer. No, action and reaction forces act on different objects, so they do not cancel each other out. Yes, bodies can move under action-reaction pairs. For example, a swimmer pushes water backward, action, and water pushes the swimmer forward, reaction. A man slips on the oily floor. He wants to move out of this area. He is alone. He throws his bag to move out of this slippery area. Asterisk. Why is it so? Answer. By throwing the bag in one direction, the man exerts a force on it, action. The bag exerts an equal and opposite force on him, reaction, pushing him in the opposite direction, helping him move out of the slippery area, Newton's third law. How would you use Newton's third law of motion and law of conservation of momentum to explain motion of rocket? Answer. Newton's third law asterisk asterisk. Rocket expels gases backward, action. Gases push the rocket forward, reaction. Conservation of momentum asterisk asterisk. Total momentum before and after remains constant. Initially, total momentum is 0. As gases move in one direction, the rocket moves in the opposite direction to conserve momentum. Why are cricket batter gloves padded with foam? Answer. The foam padding reduces the impact force of the fast-moving ball by increasing the time of contact. This lowers the force felt on the hands, impulse equals force times time, and protects them from injury. Where will your weight be greater, near Earth or near Moon? What about mass? Answer. Weight is greater near Earth because Earth's gravity is stronger. Mass remains constant everywhere, whether on Earth or Moon. When Ronaldo kicks the ball, at the highest point of ball both Earth and ball attract each other with the same magnitude of force. Why then the ball moves towards Earth and not the Earth? Answer. According to Newton's third law, both Earth and ball exert equal and opposite forces on each other. However, the Earth has a very large mass, so its acceleration is negligible. The ball has a small mass, so it accelerates more and falls towards the Earth.
Long response questions.
QI. Give an extended response to the following questions. State first law of motion. Explain with the help of examples. Why is it called law of inertia? Asterisk asterisk answer. Newton's first law of motion. In the absence of an external unbalanced force, an object at rest remains at rest and an object in motion continues in uniform motion in a straight line. This law is also called the law of inertia because it describes the natural tendency of objects to resist changes in their state of motion. Examples. A book lying on a table stays at rest until someone pushes it. A moving car stops when brakes are applied due to the force of friction, otherwise, it would keep moving. Define inertia. Why is it important to have knowledge of inertia in our daily life? Answer: inertia. It is the property of a body by virtue of which it resists any change in its state of rest or uniform motion. Types of inertia. Inertia of rest. Inertia of motion. Inertia of direction. Importance in daily life. Seat belts in cars protect passengers during sudden stops. Inertia of motion. Dust comes off a mat when it is shaken. Inertia of rest. Vehicles negotiate turns at reduced speed to avoid slipping. Inertia of direction. State and prove Newton's second law of motion. Deduce it from the first law. Answer: Newton's second law of motion. Newton's second law of motion. When a net force acts on a body, it produces acceleration in the direction of the net force. The magnitude of this acceleration is directly proportional to the net force acting on the body and inversely proportional to its mass. Prove: if a force F produces acceleration in a body of mass m, then we can state mathematically, A is proportional to F1. A is proportional to 1/m-2. A is proportional to F/m. F equals kma. K is a proportionality constant. In SI unit, the value of K is 1.
F uguale ma.
OR.
Newton's second law of motion. The rate of change of momentum of a body is directly proportional to the applied force and takes place in the direction of the force. Mathematically, F equals ma. Proof: let mass equals m, initial velocity equals u, final velocity equals v, time equals t. Change in momentum equals mvu. Rate of change in momentum equals ma, as equals a. Newton's second law. F equals ma. If F equals 0, then ma equals 0. A equals 0 as m is not equal to 0. This implies either the body at rest stays at rest, or body in motion continues in uniform motion in a straight line. This is Newton's first law. State Newton's third law of motion. Explain with examples from daily life. Answer: Newton's third law of motion. For every action, there is an equal and opposite reaction. Examples: when you jump off a boat, the boat moves backward. A rocket moves forward by expelling gas backward. A swimmer pushes water backward to move forward. State the limitations of Newton's laws of motion. Answer: limitations. Not applicable at very high speeds, close to speed of light. Not valid at atomic or subatomic levels. Only applicable in inertial frames of reference. cannot explain the behavior of particles under strong gravitational or electromagnetic fields, needs relativity or quantum mechanics. Differentiate with examples between contact and non-contact forces. Explain fundamental forces and Dr. Abdus Salam's role. Answer: contact forces. Forces that act through physical contact is called contact force. Examples: friction, tension, normal force. Non-contact forces. Forces that act without contact is called non-contact force. Asterisk examples: asterisk gravitational, electric, and magnetic forces. Fundamental forces. Gravitational force. Electromagnetic force. Strong nuclear force. 4. Weak nuclear force. Dr. Abdus Salam's role. Dr. Abdus Salam, along with Sheldon Glashow and Steven Weinberg, developed the electroweak theory in the 1970s. This theory combines the electromagnetic force and the weak nuclear force into one framework. Their work was a key breakthrough in physics, leading to the Standard Model, which explains the basic particles and their interactions. Dr. Salam won the Nobel Prize in Physics in 1979 for this important achievement. Represent the forces acting on a body using free body diagrams. Answer: a free body diagram, FBD, is a diagram showing all the forces acting on a single object. Example: for a block on a table. Weight, W, acts downward. Normal force, N, acts upward. Applied force, F, acts horizontally. Asterisk friction, F, acts opposite to the applied force. Define momentum. What is its formula and unit? Is it scalar or vector? Show that ns and kgm/s are equal. Answer: momentum, p, the product of mass and velocity of an object. P equals mv. SI unit, kgm/s or newton-second, ns. Weight. Quantity of matter possessed by the body. Force due to gravity. Constant everywhere. Changes with gravity. Scalar. Vector. Measured by balance. Measured by spring scale. Unit, kg. Unit, n. What are gravitational field and gravitational field strength? Explain. Answer: gravitational field. A gravitational field is the region around a mass where another mass experiences a force of attraction due to gravity. Gravitational field strength, G. It is the force experienced by a unit mass placed in a gravitational field. Formula: G equals, where F equals gravitational force, M equals mass of the object. Unit, slash or slash. Example: on Earth, the gravitational field strength is approximately 9.8 m/s superscript 2, meaning every 1 kilogram of mass experiences a force of 9.8 n. Justify and illustrate the use of electronic balances to measure mass. Answer: justification. Electronic balances are used for accurate and quick measurement of mass. Unlike spring balances, electronic balances measure mass directly and are not affected by gravity, making them ideal for use in labs and industries. Illustration/working. They use a load cell or electromagnetic force restoration method. When an object is placed, it causes deformation or displacement, which is converted into an electrical signal. The signal is processed and displayed as mass on the screen. Advantages: high precision, fast response, not influenced by local gravitational changes. State and prove Newton's second law of motion in terms of momentum. Answer. Statement. Momentum form. The force acting on a body is equal to the rate of change of momentum of the body. Mathematically, F equals, where P equals mv is momentum. Proof. Let initial momentum equals mu, final momentum equals mv. Change in momentum equals mv, mu. Time taken equals t minus then. F equals m. Equals ma as equals a. Thus, F equals ma, which is the commonly used form. Define isolated system. State law of conservation of linear momentum. Explain with example. Answer. Isolated system. A system on which no external force acts. Only internal forces are present. Law of conservation of linear momentum. If no external force acts on a system, the total linear momentum of the system remains constant. Mathematically, m1u1 plus m2u2 equals m1v1 plus m2v2, where m1, m2 are masses, u1, u2 are initial velocities. v1, v2 are final velocities. Example. When a gun is fired, bullet moves forward, momentum. Gun recoils backward, equal and opposite momentum. Total momentum before and after firing remains zero, if system is isolated.
Numerical.
QAV. Solve the questions given below. A boy is holding a book of 2 kilograms. How much force is he applying on the book? If he moves it up with the acceleration of 3 ms, 2, how much total force should he apply on the book? Solution. Given data, mass equals m equals 2 kilograms, acceleration equals a equals 3 ms, 2. Gravitational acceleration equals g equals 9.8 ms, 2. To find, holding force equals Fh equals? Total force equals Ft equals? We know that Fh equals mg. Fh equals 9.8 equals 19.6 nans by Newton's second law of motion. F equals ma. F equals 3 equals 6n. Now the total force acting on the book is Ft equals Fh plus F.
Ft égale 19.6 plus 6 égale 25.6 nans.
A girl of mass 30 kilograms is running with velocity of 4 ms, 1. Find her momentum. Solution. Given data, mass equals m equals 30 kilograms, velocity equals v equals 4 ms, 1 to find. Momentum equals p equals? We know that p equals mv, p equals 30, 4 equals 120 ns. A 2 kilogram steel ball moving with speed of 15 ms, 1. It hits with bulk of sand and comes to rest in 0.2 second. Find force applied by sand bulk on the ball. Solution. Given data, mass equals 2 kilograms, initial speed equals 6 equals 15 ms, 1, final speed equals vf equals 0 ms, 1 time equals increment t equals 0.2 s. To find, force equals F equals? Since the rate of change in momentum is given by F equals increment P equals PF minus pi equals M minus M. Increment T. By putting the values, F equals minus 150 nans. 0.2. Here, negative sign indicates that force will be opposite to the direction of the motion. A 100 grams bullet is fired from 5 kilograms gun. Muzzle velocity of bullet is 20 ms, 1. Find recoil velocity of the gun. Given data, mass of bullet equals mv equals 100 g equals 0.1 kilograms. Mass of gun equals mg equals 5 kilograms. Velocity of bullet equals vb equals 20 ms. 1 to find. Velocity of gun equals vg equals. Solution. By law of conservation of momentum. Momentum before firing equals momentum after firing. Or momentum after firing equals momentum before firing. PB plus PG, after equals 0 as P equals MV, so MVB plus MGV equals 0. 0.1 by 20 plus 5x VG equals 0.
2 pluss 5x VG er lik 0. 5 VG er lik 2.
VG égale 0.4 ans.
5. A robotic car of 15 kilograms is moving with 25 ms. 1. Brakes are applied to stop it. Brakes apply constant force of 50 N. How long does the car take to stop? Solution. Given data, mass equals m equals 15 kilograms, initial speed equals 6 equals 25 ms, 1 final speed equals vf equals 0 ms, 1, force equals 50 N. Opposing, to find, time equals t equals. Increment p as the rate of change of momentum is given by f equals. Increment t. pf minus pi. F equals. Increment t. Or. pf minus pi. Increment t equals. F. Increment t equals minus mm. By P equals MV. Increment T equals. Increment T equals. Minus 50. Increment T equals